This is Chapter 13, Section 2. We will break it into an A and a B part. We're going to be talking about colligative properties today and how to do some initial calculations. You do need your periodic table, a calculator. If you were in class, I also gave you a table that's going to be introduced today. And if you are online, that table will be put into Google Classroom. So, colligative properties. These are properties that depend on the concentration of your solute particles. Remember, solute, that is the substance you are dissolving into your solvent. So, the four colligative properties are going to be vapor pressure lowering, freezing point depression. Both of those we will talk about today as far as 13.2 Part A, and then in 13.2 Part B, we will talk about osmotic pressure and the vapor pressure lowering. Okay. Vapor pressure lowering is also today. So, a non-volatile substance, non-volatile, is one that has little tendency to become a gas under existing conditions. So, your boiling point and freezing point of a solution will differ from those of your pure solvent. The easiest thing to think about here is, let's say you take water and you want to boil it or freeze it. You know, water's boiling point is 100 degrees Celsius, its freezing point is 0 degrees Celsius. But if you add an impurity to it, so a solute into this water, that solute will change the boiling and freezing point. So it will elevate the boiling point and it will lower the freezing point. A non-volatile solute will, again, raise your boiling point and lower your freezing point. This picture is in our book. We're going to go about drawing this in your notes, and I'll do a separate drawing too. So make sure that you have this. It's going to be needed in your homework, and again, give the details there in your notes too. So this is going to be vapor pressure on this side for the y-axis, and temperature in degrees Celsius on your x-axis. And if we were to look at a pure solvent, and for the pure solvent, I'm just going to leave it as a black line. If you remember our phase diagrams that we had, we come up, we hit our triple point, and then you had two other marks that went basically up like this for water. You have what is going to be your normal boiling point that I am going to mark right here. Man, this is not drawn very good, but that's what we get. So here's your normal boiling point. This will be your normal freezing point right here. So TF and TB. And again, in this part, I'm just changing my colors. We have a gas that's in this section. We have liquid in this section. And then we have our solid over here in this section. So in black, we have looked at our pure solvent. Pure solvent. I'll change it over to blue because I think they use blue in the figure. If we were to add a non-volatile solute to this, so an impurity to it, it is going to change. So our triple point is going to come down, and we will get new boiling and freezing points. So if I come right down here with this, this is our new boiling point. This is going to be when we add our solution, our non-volatile solute. And a new freezing point too. So it does lower that freezing point that we have right there. The difference in these, so from here to here, we are going to call that delta TB. So that delta symbol means a change in. So we do have a change in the boiling point between the pure solvent and the solution. And then we also have a change in our freezing point to delta TF. So again, make sure you have all of this in your notes, and the picture was also earlier too. And we'll be working with this change in temperature and some calculations that we'll do. So vapor pressure of pure water and a water solution. Again, the solution means that a solute has been introduced into this. So on the left, we've got pure water. You can see that the vapor pressure of water is going to be greater than the vapor pressure of water over an aqueous solution. So we have more molecules here in the top of this one and fewer molecules over there once our solute has been introduced to the solution. So the vapor pressure lowering that you have here once you added a non-volatile solute. And we also talk about Raoult's law whenever we talk about this. So if you hear any mention of Raoult's law, that's what this is referring to. So freezing point depression, another of our colligative properties. It's the difference between the freezing point of a pure solvent and a solution. It says of a non-electrolyte in that solvent. And this change in temperature is going to be directly proportional to the molal concentration of the solution. So we've got to come up with, well, how do we find the molal concentration of the solution? The molal freezing point constant. So here's some constants, or Kf, is the freezing point depression of a solvent in a 1 molal solution of a non-volatile, non-electrolyte solute. And our formula that we're going to use for today, which we will slightly modify a little bit later on. So change in temperature is equal to this constant times the molality of a substance. So that lowercase m is the molality of a substance. Since we are talking about non-electrolytes, because we will, before this chapter is over with, we will talk about electrolytes. But for now, non-electrolytes do not break apart in solution. So if it's a non-electrolyte, we don't have to consider it any further within our calculations. It will not change our calculations. So Kf is a constant. I'm going to show you here just a second the table that I've either given out or is online for you to look at. You don't need to memorize these constants. And then molality, it is a value that we will have to calculate. So if I'm refreshing your memory on molality, it is the moles of solute over kilograms of solvents. So moles of solute over kilograms of solvent is how you find molality. And our change in temperature will be in degrees Celsius, because all of these Kf values are based off of the Celsius temperature scale. So here we have 6 different solvents that we're looking at. You can see it's basically broken up into everything dealing with the freezing point. It's normal freezing point and it's molal constant. And then you've got your normal boiling point and the molal boiling point constant, or Kb. So there is a Kf, there is a Kb that'll go with a boiling point elevation, and these are the values that we're looking at here. So again, you don't need to memorize these, but you do have to know how to use them and where the information is to be found whenever you need them. I don't have my videos working right now, but I know in this video, whenever you add, for our freezing point depression, whenever you add a solute to whatever your solvent is, it does make it more difficult to form a solid network whenever you are trying to go from that liquid to that solid. As far as liquid, you freeze it, obviously freezing point depression, to get to your solid phase. And again, it does make it more difficult to form the solid network. That's why the freezing point is lowered. So here's an example problem. Again, in your notes, you're writing down the examples and showing all the work to solve for them. What is the freezing point depression of water in a solution of 17.1 grams of sucrose? They gave you the formula for sucrose and 200 grams of water. And then it wants to know what is the actual freezing point of the solution. So the first thing that we're going to have to calculate, freezing point depression, so delta TF, using what we just saw earlier. And then you're going to find the actual freezing point. So for the actual freezing point, we are going to take whatever the normal freezing point is and add on delta TF to find out what our new freezing point is then. So we do have a couple of different steps, and also too that little m is for molality, so it looks like we're going to have to calculate the molality too before we can actually calculate delta TF. So let's get to these calculations. So I've rewritten down the m for molality. We know we have to have that to find delta TF, since that's based on the constant, or along with the constant, and then we will put it into our new calculation for the new freezing point of the solution. Freezing point new, again, freezing point of our solvent plus delta TF. So if I go back up there to molality, moles of solute is not given. We were given 200 grams of water, 17.1 grams of sucrose, and again it's solute and solvent, so sucrose is the solute. We have to find out its moles first. I showed you a couple different ways back in the previous chapter on how to do that. It is up to you how you want to show that work, but make sure you show all of it. So off to the side, I'm going to do 17.1 grams of sucrose. And we are going from grams to moles. Again, I'm looking at just how much space I have. I'm not writing out the word sucrose, but I am dealing with our solute right now, which is sucrose. The molar mass of sucrose, once you use your periodic table to find it, is 342.34 grams. And once you take your 17.1 divided by the 342.34 grams, you will get 0.05 moles. And I am going ahead and round it off there. It's like 0.04995, so I'm going to go ahead and put 0.05 moles in here at the top. So I have taken this and I am plugging it back in right over there. And then we divide by that by kilograms of solvent. They gave us in the problem 200 grams of water. Once you convert grams to kilograms, that is 0.2 kilograms of our solvent. So 0.05 divided by 0.2 is 0.25 is going to be our molality. So we can take that and plug it into the next step. Plug it in right down there. Our delta KF molality again is 0.25. And if we go look at our freezing point constant of water, so the freezing point constant has to be of your solvent. Again, solvent, solvent, solvent is water in this case. And when I go look at my table, the freezing point constant for water is negative 1.86. So make sure that negative is there, and that is degrees Celsius over molality. So notice your molality units do cancel once you put all this together. And multiply that times negative 1.86, and you get negative 0.465 degrees Celsius. That is our delta TF, or change in temperature for the freezing point. Now we're ready to take that and plug it into delta TF for the next part. And our new freezing point, if I go back and look at my chart for freezing point of the solvent, that's our normal freezing point of the solvent. Water is 0.00 degrees Celsius, plus we are adding on the negative 0.465 degrees Celsius. So our new freezing point is negative 0.465 degrees Celsius. So they are saying if you add sugar to water, and in this case 7.1 grams of sugar to 200 grams of water, it will drop the freezing point of water by about 0.5 degree Celsius. So freezing point depression. Please make sure you show all of this work for these types of problems. Make sure you understand the flow of the problem too, what is being asked for, and the steps to get there. Now we're going to look at boiling point elevation. The math is going to be just the same as the previous one, based off the same principles. So boiling point elevation is the difference in boiling point of the pure solvent and a non-electrolyte solution of that solvent. So it's saying you've added an impurity or a solute to your solvent, and it is directly related to the mole concentration of the solution. So again, same equation, but instead of the subscript F, we have a subscript B, as you see right here at the bottom. Little m is still for molality. The Kb values are still in the chart that you were given or that you've seen already in the PowerPoint. So let's go make a calculation here. Write this problem down. What is the boiling point elevation of a solution made of 20.1 grams of non-electrolyte solute? Again, that non-electrolyte, it just means that particular solute is not going to break apart into solution. So it doesn't change our boiling point any more than what an electrolyte would. So 20.1 grams of solute into 400 grams of water, and the molar mass of the solute is 62 grams. Notice it gave us the molar mass of the solute, but it doesn't actually give us what the solute is. But based on the values, we're going to be able to calculate molality. So let's go work this out. Again, if I wanted to do molality first, because our goal is to find just the boiling point elevation. So we're going to find delta TB, which is Kb times M. It does not ask for the new boiling point. It just asks for the boiling point elevation. So that's that change in temperature. So again, be really careful what your questions are actually asking for. We don't have to do as much work on this one, but molality, we know we've got to calculate that. That is moles of solute over kilograms of solvent. By the way, our solvent is still water in this case. So, moles of solute, if I need to get it really quick, I know that we have 20.1 grams of solute, and when I convert grams to moles, I don't know what the substance is, but it says that the molar mass of this solute is 62 grams. So doing my math here, I get a molality of 0.324. So I'm going to plug that in right over here. Again, plug it in, 0.324 moles. Kilograms of water, it tells us that we have 400 grams of water, so that is 0.4 kilograms. So the molality is 0.324 divided by the 0.4. And we get 0.81 moles per kilogram for molality. We're going to use this, plug it into the next spot right here. Delta TB, boiling point elevation. If I find my Kb from the chart for water, the molar boiling point constant for water is 0.51 degrees Celsius over molality. And the molality that we calculated is 0.81. So our change in boiling point, or the boiling point elevation, is again almost a half a degree. I've got 0.41 degrees Celsius. So adding that solute to the water raised the boiling point of the water about a half a degree. If I asked you for the new boiling point of water, it would be the normal boiling point of 100 plus the 0.41, so 100.41 degrees Celsius. So make sure you get all of this math written down, and that's going to be the end of section A for us, 13.1a.